Physics 2211, lab number 2. Okay, so what's the purpose of this specific lab? So in this lab, we're dropping an object from a certain height and seeing how the force of drag affects how it falls. So the relevant equations in this lab are going to be the force of gravity, which is obviously just negative mg in the y direction. We're going to be using that kinematic equation to do some position and velocity update equations, and yeah, also the other kinematic equation right here. Okay, so the models that are being used. So for the real life observation, we're using the tracker program. As you can see, it's right here. And then the predicted observation with gravity only and the predicted observation with gravity and drag. We're both using glow script models. So here's gravity only, and then here's gravity and drag. So you can already see that the gravity and drag model looks a lot more like the real life observation than the gravity only model. Okay, so the initial conditions are the system I'm using is a plastic plate and it's facing downwards. The surroundings that are acting on the system are the earth and the air surrounding the plate. The initial velocity is 0 meters per second, and the total height fallen in the video is 1.91 meters. Okay, so for the experiment itself, as I just said, I dropped a plastic plate facing down a distance of 1.91 meters. And I recorded the motion using the tracker app. So here's a little bit of a more close-up view of this actual graph. As you can see, it's starting to increase speed, and then it kind of starts to level off here due to the drag as it gets closer to maximum velocity. Okay, so for the models, really what I did is you can't see it in the screenshot, but I altered the mass. So it was about 6 grams or so, I would want to say. And then, so this is a screenshot of the position first time with the drag included in it. So basically the only difference between this and the other glow script code is I just don't have the force of drag in here. So you can see I calculated B and got that nice number right there. And then to get force of drag, I just basically multiplied v hat, which is that vector right there, times speed squared times negative b, just like the equation given. So I have speed right there, which is basically just the y component of velocity. Then here's the force of gravity right here. Then here's net force, and then these are the two update equations that I was talking about earlier in the video. So this is the velocity update, and then here's the position update. So these are just the code versions of the kinematic equations right here. So yeah, that's how I kind of did the code. Okay, so the comparison of the 3 graphs. So as we can see right off the bat, the predicted position with the gravity only is a lot worse than the predicted position with the gravity and drag. So this blue line right here is the gravity and drag line. And so, yeah, as you can see, it's right on the orange line, which is the observed position, the real-life model. You can see it's right on the line. It kind of splits here at the end a little bit, but it's pretty close to what the actual plate did in real life. Whereas this one, where we're not accounting for drag, it obviously just keeps speeding up forever, and it just kind of goes way too fast. Okay, so what does this all mean? So basically, the model that includes drag obviously shows velocity reaching a terminal velocity. So here's without drag, the velocity just kind of keeps speeding up forever and ever, whereas this one kind of levels off at about negative 3.7 meters per second. At terminal velocity, F net equals 0 because the force of gravity and the force of drag are equal and opposite. Okay, so what if the terminal velocity, or what if the initial velocity was not 0? Would the terminal velocity change? Short answer, no. So as you can see, both models, the terminal velocity kind of levels out at about negative 3.7 meters per second. This model up here, starts at negative 1.5 meters per second, and then this one, it starts at 0, but no matter what, because the no other parts of the terminal velocity equation changed, they should equal out to the force of gravity in the end, and reach that same velocity so that the forces cancel out and the overall force is zero. Okay, so some possible sources of error. There were some moving air in my dorm room from the fans and air conditioning unit, and there was some inaccurate measure. There might have been some inaccurate measurements from how far the plate fell. Thank you so much.